Thank you very much. I'm glad everyone came here first thing in the morning, and this is going to be an interesting talk. I have a whole bunch of things to talk about, and I probably won't get through everything. But we've been looking at an analysis of our workloads. We have a number of what we call proxy apps. There's things that are sort of like benchmarks, stripped down to applications. And we've been working on integrating these into LLVM's test suite. That's the first thing I'll mention. We have a number of these now in LLVM's test suite. And so we've been looking at them in this context and trying to identify opportunities where LLVM and Clang could do a better job compared to other compilers, compared to GCC, compared to Intel compiler, compared to other vendor compilers that we use. And so this talk is going to be kind of a smattering of things. And I'm going to try and sort of walk through in some order, where we sort of start with low-level things and kind of work our way up to high-level things. Some of these things will apply specifically to DOE proxy apps, and some of them will apply more generally. All right. So let me start with a story. And the story has to do with actually, first I should back up and say that the work that's being presented here is the work of myself, Brian Homerding, and also Michael Cruz. So now, okay. So there's the story, and the story starts something like this. So I've been working on LLVM for a long time now. And obviously, when you're working on LLVM and you make changes, it's important to run benchmarks and make sure that you're making things better and not worse. So to do that, I would often use LLVM's test suite and run performance comparisons. And since I am lucky enough to be in a national lab and we have a number of nice build machines that we can use, and I can run the test suite in a way that's highly parallelized, that's often what I do. And in fact, although running the test suite in parallel makes the results noisier in some sense, if you have enough cores, you can run enough times to get enough statistics that, statistically speaking, this is OK. You can still get very meaningful results. Now, when Brian started working on this project, he also started doing performance comparisons, and he started running the test suite in this sort of way that you normally do it when you're doing performance benchmarking. You try to make the machine very quiet, and you run everything. And we started getting some really interesting discrepancies. And this was confusing us. So, and we don't quite have a good answer to this, but let me sort of explain what's going on. So here I'm going to present some data looking at the performance of LLVM's test suite compiled using Clang and compiled using GCC. These are essentially Clang trunk in the latest GCC release. And this was on, I think the particular results that I'm going to show you were on a Broadwell system. We've repeated these results recently on Skylake, and they're essentially the same. And so here, so what we do is we run the test suite multiple times. In this case, we run the whole thing 30 times in each configuration, and then for each test, thus you get 30 samples. So you have 60 samples in total in 2 classes. And then we use this nice little utility called Ministat, which you can find on GitHub or what have you. There's also a Python version of Ministat, which is quite convenient. And this performs a t-test with some confidence interval, and so it will give you a difference with some error bars, which is quite nice. And so that's what we do. We then remove some outliers. There are some outliers because they're just not good performance benchmarks. They're unit tests. We have a couple of other outliers that are things like testing built-in intrinsics that Clang has and GCC doesn't. So the GCC version runs infinitely fast because it just prints the answer, and the Clang version runs a test. But in any case, so here's the sort of interesting thing that we found. There are a number of tests, and here we've picked out some of the proxy apps, although if you look across the test suite, and I'll show you in a minute, this is a sort of generic feature, is that there are statistically significant differences in the sort of the relative timings of tests, either when the test is run on the sort of relatively quiet configuration, where you're running one test at a time, and in a configuration where you're running, you're using all the hardware threads on the machine, essentially. And the unfortunate, so far sad conclusion is that essentially these differences tend to favor GCC over Clang. And so here you can see here. So when you're running multiple tests at a time, GCC here tends to be faster and faster here, and here and there and there and there. Whereas on the quiet system, the differences are much smaller, or they tend to favor Clang and LLVM. So this is obviously something we thought was odd. And then so we started thinking about what kinds of things could cause this. So the tests themselves are the same. They're running the same input sets. Effects from the memory subsystem, data cache pressure, these kinds of things should all be the same between the different tests because they're running the same thing. Oh, also I should mention that especially because many of these proxy apps from the DOE support OpenMP, we also thought at first, well, maybe it's just that when you're running multiple threads, there's a difference. And it turns out the answer is no. So with many of the things, if you take a single application and just run it using multiple threads over all the hardware threads on the machine, all the cores on the machine, then the differences here look just like the single test at a time results. So those tend to favor Clang. It's only when you're running on a system where the system is running lots of different applications that you get results that tend to favor GCC. And so, as I said, we started thinking about what kinds of effects could cause this. There are some things. But here, let me just show you. This is the plot. I mean, obviously, there's nothing really here for you to read. But here's a plot of sort of all the tests in the test suite, minus the outliers. And so, I mean, I say it favors GCC. It's not, in some sense, it's a sort of slight bias over the entire test suite. Although on the workloads in which we're particularly interested, it's actually more significant. So this is sort of one of the things that we have been looking at in some detail. In any case, so we started thinking like, well, what kinds of things could cause it? So it has to be something to do with the code generation, because what the program is doing and the data access patterns and such, those aren't different between the different compilers. But there obviously are things that can differ between compilers that can cause these kinds of effects. So, for example, if LLVM is producing code which is more demanding on the instruction cache than GCC's code, or is more demanding on the branch prediction resources, or other kinds of resources that tend to be shared in non-uniform ways across different applications as they're running on the machine, then that can cause this kind of difference. And so I don't, originally I was hoping that we would have a good answer for you with a nice breakdown. At this point we don't yet, but we have started looking at this to try and figure out what's causing this difference. And so I'll just present one example of a thing. Which is the, excuse me, which is we looked at the sort of relevant instruction cache miss rates. So this plot is sort of somewhat misleading actually because it's plotting percentage change, but let me just sort of blow up here. And so here, this is the sort of tests on the high end of the difference scale, and we wanted to see like, well, does it look like there's a correlation between the relevant difference in the instruction cache miss rates and the difference in the performance between the different configurations? And the answer is yes. I mean, it is on this set a statistically significant correlation, but it's certainly not the only factor. And so this is one thing that we are going to continue to look into to try and see if we can pin down what these differences actually are. It seems like this is one of the relevant effects, but as I mentioned, there are definitely other kinds of effects. Well, I mean, there are other kinds of effects that we know about. I mentioned like instruction cache, branch prediction resources, et cetera, and perhaps some things we don't know about yet that could be causing these differences. And so this is something that we are investigating. But this is, in some sense, one of the most interesting things that we found. And you know, one of the things that's sort of interesting about this, I should say, is you know, as we look at our workloads, a lot of our workloads don't tend to look like this. In HPC, you know, we tend to run in a mode where each user kind of gets a node or some set of nodes, and they run a single application on those resources for some fixed period of time. But we do have applications that are more dynamic, that, you know, run lots of different things. They use like a task-based system, something that's closer to what you see in a sort of microservice model. And there, this kind of thing is a lot more relevant, because there you have a lot of different pieces of code that are all running at the same time on different cores. And so understanding these kinds of effects is really kind of important for understanding the performance of these more dynamic kind of multi-physics type of workloads that we talk about. OK, good. So now we're going to go up a notch. Let me talk about something else. So as I said, so we're doing this performance analysis, and you know, for some of these things, I mean, there are things that are more mundane that cause performance differences. I'm going to talk about one thing here that we have. We're developing particular plans to fix. So here, this is a very simple example. We have here, this is one of the applications, which is now in the test suite. It's RSBench, and inside RSBench, there's the hot kernel here. In some sense, looks uninteresting. It looks like this, and the reason I say it's in some sense uninteresting is because obviously there's going to be a lot of time that's spent in these trigonometric functions, and so you might think, well, there's not actually much the compiler is going to do here, because the performance is going to be heavily determined by the performance of these trigonometric functions. And that's kind of true, except that it's not, because there's this important combination here, and this is something the compiler needs to deal with. Because in the C library, there are indeed you know, separate sine and cosine calls, but here, Clang calls sine and Clang calls cosine. But if you run under GCC, it's nice enough to make this a sine cosine function call. And now some of you might be saying, yeah, but Clang knows how to do that too, so why didn't it? And the answer is that we don't get to compile this application with fast math mode turned on. And so when you run under Linux or under some other systems where these calls can you know, set everyone's favorite variable, which is errno, which you know, makes all of the math functions not side effect free, then Clang doesn't do this transformation. But GCC does do this transformation. And it turns out that if you're smart about this, even if these calls set errno, you can still do the transformation by understanding something very specific about the semantics of these particular calls, which is that their defined error ranges and errno error codes and everything else are precisely the same for their arguments. And so sine and cosine, you know, the sine cosine function also sets errno in exactly the same way. And so long as you're not, you know, so long as you're calling both of these things and there's nothing kind of in between, or there's nothing else in between that could set errno and that you might be reading, even if these things are side effect, you know, even if these instructions, these calls have side effects because they set errno, you can still do this replacement. But the infrastructure that we have in LLVM currently doesn't support that. And as I said, the way that you do this has to be a little bit more complicated, because you need to actually look to see that there aren't other things in between you have to do a sort of more complicated set of legality checks. And right now, we just have a kind of simple way of doing this during instruction selection that does this transformation, but it relies on the fact that we're not operating a mode in which the calls have side effects. Okay. And so there are a bunch of things that we can do in this case to make this better. And I think it's sort of mostly broken down here. And I've broken it down here in a set of sort of generic improvements that will hopefully be helpful. So one is we have a concept of write-only functions, but we don't have a way of marking them. And the other thing is that most of these math functions are essentially write-only. So they may set error no, but they don't read it in any meaningful way. And so we can actually represent that to the optimizer, which we don't currently. And then once we do that, then you can kind of write a sort of generic optimization path which will look for these sine-cosine pairs and do the sine-cosine replacement. Again, it's a special case, but it turns out that it's a fairly important special case. And so doing that even when fast math mode is not enabled is something that we would like to do and should do. There are some sort of infrastructure improvements that we'll make in order to make that happen in a reasonable way. Okay. Next thing. This is hopefully entertaining. So we have a bunch of these proxy apps. And if you look in the test suite, you'll see that a number of these proxy apps have a whole bunch of various pragmas in them. These are mostly made to represent the pragmas that exist in the real code in the full applications from which these things were extracted. And so we had a sort of obvious question, which was, do these things make a big difference? Because obviously when you add these things into LLVM's test suite and when you test them with Clang, then Clang isn't going to do anything with these pragmas, especially because most of them don't even just exist in the code. They actually exist in the code guarded by various preprocessor macros. So it's not even just a matter of saying like, well, we could add these pragmas to Clang if they made a difference, because our programmers are really smart and decided that they really don't like ignored pragma warnings, because no one likes those. And so they've guarded all these things with preprocessor macros, which is kind of cool. But on the other hand, it means that the process of adding these pragmas to Clang would not actually be as automatic. I mean, we could add them, but getting applications to use them would still require source code changes. That's the first thing to realize. On the other hand, I think it's a really nice argument in some sense against adding lots of different pragmas from different compilers, and instead just sort of extending the pragmas that we have in Clang scheme, because if people have to make source code changes to enable using the pragmas in Clang scheme anyway, then we might as well have something that's consistent. In any case, so we had this question, which was, how big of a difference do these things make? And so here I'm just going to present one example. This is mini-FE, which is a relatively important proxy in the suite to our workloads, and it was picked because we have there are a significant number of these pragmas that are in the source code, and we weren't quite sure how much they mattered. So here we figured this out. The answer is they don't matter at all. So this is the Intel compiler. I think this is Intel 17, so I mean I should be fair and say it's possible that they did matter at some point. This proxy has been around for many years, but at least using a relatively recent version of the Intel compiler, which in principle supports all of these various things, it turns out that it doesn't make any difference. And these results were run on a Haswell box, but we also tried this on Skylake, and it's the same. So okay, and there's Clang. And so in this case, I don't have much to talk about, because actually it does a little bit better than the Intel compiler on this proxy, so that makes us all smile. Okay, and yeah, so I mean I showed this one example, but I should say that we ran a whole bunch of these tests, and for some of them the pragmas do matter, but actually in a lot of cases the pragmas don't seem to make much of a difference, and so this leads to a sort of interesting set of questions, because now we're not quite sure why they're there. they could be there because they mattered in an older version of the compiler. They could be there because in the application from which the proxy was extracted, the pragmas mattered. But in the proxy, the code is simple enough for the compiler to figure out what's going on. Or there are fewer checks you have to generate for multi-versioning, or a number of other things. So this is sort of an interesting question now because we have the code that's littered with these things and we're not sure why. So that's something that we're going to have to figure out. Let me sort of switch for a minute and tell you something interesting about the test suite. Another nice set of benchmarks that we have, which we've now added to the test suite, is called LLVM. For those of you who have been around for a while or sort of otherwise know about this, you'll know that there's a kind of historic benchmark that's called the Livermore loops suite, which you can still find on netlib or something. The folks at Livermore actually have a nice updated version of this called LLVM, which is written in modern C++. And not only that, but it's written in modern C++ or quasi-modern C++ in lots of different ways. So they have the benchmarks that use lambdas and use functors and use different techniques. And so it's nice because you can it tests different ways that the compiler needs to remove abstraction penalties, essentially, for a bunch of different loops. And there are lots of different loops. So if you take the benchmark itself and just run it, it runs for a really long time. So which is it's good in the sense that it runs a long time because it has a lot of different loops in different configurations. But on the other hand, it means that if you just add a single binary to the test suite, you're not really going to see any interesting performance changes because each individual loop doesn't really run long enough to make a significant impact on the running time of the binary. And so the only kind of changes you'd end up seeing is if you really screwed something up and it made huge swaths of the test slower. So that's not really very interesting. What we'd like to be able to do is to track the performance of the individual kernels over time as we make changes to the compiler. So what Brian did was he took this benchmark and he kind of ripped out the driver portion of it and replaced it with the Google Benchmark library. So we already have the Google Benchmark library in the test suite. It is used for some of the X-ray tests, the micro benchmarks that are in there. And so what we did was we reused and then improved that infrastructure so that we can add the benchmark into the benchmark test suite. We can use the Google Benchmark library. And for those of you who don't know, I should say one of the nice things about the Google Benchmark library is that it will run each kernel a dynamic number of times. So it runs. I mean, there are thresholds on this, but it will run until it gets a sort of stable timing number for a particular kernel and then move on. And that's really nice because it means that you don't have to choose a sort of conservative overestimate of the number of times you need to run the kernel to get good timing. And so the whole thing actually runs much faster, and we get better statistics out of the set of micro benchmarks. So that's nice. And the only problem was that it used to be that the lit test driver only wanted essentially to get one result per test, and so there wasn't really a good way of integrating this. So so what Brian did was he took lit and he extended it to support sort of micro benchmark test results. So essentially each test can now report lots of different timings, and those can all get sucked up and put into LNT, et cetera. So and at this point, the procedure for adding these things to the test suite is fairly straightforward. I think this is enabled by default, so hopefully we'll do that soon. But the infrastructure is now in tree, and so if you want to add one of these things, all you need to do is sort of do you could just do what LLVM does. But essentially, there's a test suite / micro benchmarks into which you can add your benchmark to do kernel timings, and then you have a sort of fairly simple thing you put in the CMake file, and then this will work. So that's pretty cool. All right. All right. So now move up to the high level things. So one of the things we've been looking at as we look at our various workloads are loop transformations. And traditionally, one of the places where LLVM and Clang have been weakest is in our loop transformation infrastructure. We don't have too much of this, and it's one of the places where the vendor compilers tend to do a lot better than the open source compilers. So so we're looking at this in sort of two ways. So one way is that we want users to be able to direct the compiler to perform loop transformations, so they don't have to do this by hand. This is actually a really important use case for us. We would like also the compiler to be able to automatically perform loop transformations where that's helpful, and obviously produce better code. That's also important. But for a lot of loop transformations, it's hard for the compiler to perform complicated loop transformations in general, purely given the static information that we tend to give the compiler. In most real codes, a significant body of loops have dynamic trip counts, so you don't really know how often the loops execute. You also don't necessarily know how large the working set sizes are, so you don't know if they all fit in the L2 cache or if they're pulling out of memory. It's really hard to know exactly what the bandwidth bounds are, etc. Given good profiling information, you can figure some of this stuff out. But for the majority of your codes, they don't use that yet. And so there's a significant amount of tuning that has to go on. That tuning can either be done using tools. At the labs, we have infrastructure for doing auto-tuning tools. We're also working on improving that. And also, people tune things by hand. OK. So one of the things that we did was we started looking at what are the loop pragmas that are used across the various compilers, and how do they map to Clang. So of course, I just finished telling you that when we looked at the loop pragmas in the test suite, many of them didn't do anything. So in some sense, you might find this kind of funny. But I can assure you that on real applications, these things do matter. And moreover, a lot of the loop pragmas that are in the test suite are sort of relatively simple things. Things that say this loop has loop iterations that are independent, or please vectorize this. And for those, what the compiler can figure out is often much better than in the cases where you want the compiler to perform kind of higher level transformations. Where you want it to perform loop distribution or tiling, skewing, this kind of thing, where you really need to know things about the working set in order to figure out what's profitable. All right, so here's a sort of quick overview of some of the pragmas that exist, and so we're trying to think about how we can integrate and then how we can implement these in a framework inside LLVM that will let us do these kinds of transformations. So what we're thinking about is coming up with a kind of generic syntax, and I'll show you why in just a second, to represent different loop transformations in Clang and LLVM. Our current syntax, I should point out, looks more or less like this. So we have pragma, Clang, loop, and then there are things like vectorize and distribute, but there aren't very many of them. There are only like 3, I think. Vectorize, unroll, and distribute. And we have a whole bunch more that we'd like to add. Now, here, this is the Clang syntax. And in order to actually represent this in LLVM, we would do the same thing that we do currently, which is these pragmas get turned into metadata. That metadata appears in the IR and then gets passed to the transformation passes. And so if you look at what kinds of transformations do we see over our code bases, we've sort of broken it down into a set of things that we do. And you might say, well, where do these come from? In some sense, we looked at what kinds of transformations do the auto-tuners do to code. Because one of the goals here is to provide an interface that the auto-tuners can use. And this sort of breaks down along these lines. We also have, in various compilers, we have some various subsets of these kinds of things, and we talk to people and see what they actually wanted to do. That was one thing. One thing that's sort of interesting to realize about this is that some of these transformations actually generate new loops, and you want to apply several transformations to a particular loop. So, from a sort of purely user interface perspective, you have to figure out how to make that work. And so what ends up happening is, so when you have a transformation that generates new loops, it's not really clear how you would provide pragmas to say what happens to the different loops. And so that's something that we have to look at. What we've essentially come up with is a scheme via which you name things. So, okay, this is probably the obvious solution, but nevertheless, for transformations that generate multiple things, you can generate names for those things, and then you can reference those names when you provide more pragmas, and thus provide a way of sort of naming the outputs and naming the inputs and be able to do that. So obviously there are a whole bunch of questions here. We'll talk more about this on the mailing list. There are some challenges, but we're actually quite excited about providing these features to our users, because this is one of the things that we've been asked for a lot, is to have better loop transformations, and specifically not only better automatic transformations, but better transformations that users can directly control. All right. So one of the things that we've been looking at is kind of interesting. One of the things that we've been looking at is can we prototype an infrastructure for doing this using Poly? So Poly, for those of you who don't know, is the polyhedral loop transformation framework. That's a subproject of LLVM, and we would like to be able to have to be able to sort of refactor it in a way that we have a generic set of infrastructure, modular infrastructure pieces that can be reused by different transformations. So generically, what we're thinking about are, I would say, 3 pieces. So one is loop dependence analysis as a sort of independent utility. The second is a loop transformation infrastructure. And the third is the sort of automated scheduling piece that you normally associate with polyhedral loop optimizations. The automatic scheduling piece is tricky because that's where the cost modeling goes. And there are other reasons why that's tricky too. But the nice thing is that there are these other pieces that we can use for implementing optimizations in a kind of traditional way, but in hopefully a succinct way, where the infrastructure takes care of actually doing the loop rewriting, takes care of updating the analyses that have to be kept updated, the loop info and the denominator tree and all this other stuff, which I have to say, having implemented some of these optimizations, is normally the trickiest part. So that's something I think to keep in mind. In any case, so we started trying to prototype this infrastructure using Poly, and so here what I've highlighted on the next few slides is some of the things that Poly doesn't handle, that we would kind of like the infrastructure to be able to handle in order to sort of fit our vision of having a easy-to-use loop transformation infrastructure that we can use to implement these various optimizations. And some of these we sort of, these are all sort of simple examples, but we've pulled these out of real applications, and they look things like this. So these things are actually, so this actually comes up all the time, where you have a sort of dynamic inner loop count. And there are a whole bunch of other things. You can look at these slides later as you'd like. Some of these things are obviously problematic in general, like things that have conditional exceptional behavior. But needless to say, there are a whole number of things that we need to be able to handle that Poly currently doesn't handle because of its modeling constraints. So one of the things that we've started working on is sort of prototyping a way of constructing a loop optimization framework that doesn't have these constraints, that is sort of built more directly on top of the underlying loop info analysis, and provides a way of producing this sort of set of utilities that can be used for loop transformations that don't have built in the constraints that Poly currently has for handling loops. So I'm not going to have time to talk about this in any great detail, but we have a kind of at least a generic idea of how we can do this, the kind of data structures that we can use to represent things, and allow people to easily write loop transformations that will apply to a highly general class of loops, and I mean, hopefully all the cases that are interesting, and thus enable LLVM to develop a more advanced loop transformation infrastructure in a way which is maintainable and easy to enhance. Okay. So not only can you do generic things, we have, those are useful idioms. I think I'm probably going to stop there since I am out of time. Oh, and also I'll mention there's that sort of tie-in here to the vPlan work that Intel is working on potentially, and we've thought about how to do that as well. All right. So with that, thank you very much.
Thank you. We have now 5 minutes for questions.
You didn't mention OpenMP SIMD directives, Hal, which seemed rather relevant. The only OpenMP directive you mentioned was pragmas parallel 4. Whereas the SIMD is a huge pile of complexity for vectorization. How does that fit into your general scheme?
So, I mean, OpenMP SIMD is certainly very heavily used. I think as I showed in the test suite, a lot of the cases of OpenMP SIMD aren't needed because the compiler can figure it out anyway. But in real applications, this is definitely quite important. And I don't think we have any plans to touch that, essentially. So we would like people to use portable pragmas where they exist, and that's what we encourage people to do. Some of these loop transformation pragmas could, in fact, turn into proposals for the OpenMP Standards Committee to add. Branas, in particular, seems very interested in this, so we'll see. And so, my hope is that if this proves successful, then some additional subset of this may actually end up in OpenMP, and thus in the kind of portable set of pragmas that people can use.
I have basically 2 questions. For the first part, where you were seeing variations, run-to-run variations, did you track the power usage of your programs and whether they were hitting the the power curve of your systems, so that if it hits, it'll reduce your clock speeds? Whether you have run any of the power utilities and check them. So the first one.
That's a good question. So no, I suspect that when the machine is running only one core, that the clock speed is higher, and when you're using all the cores, the clock speed is lower. But we haven't checked that.
Okay. The second part is it's good to see that you are having an effort on the loop transform side. Our recent experience with Poly, though, is we hit many more than what you are showing here, and we were unable to use the Poly. So I think there are a lot of other people who are just writing their own loop transform frameworks, but if it comes to it, it'll be good. It's just a comment.
Yeah, I mean, I think this is a very good point. We've definitely run it. Well, yeah, we've run into these and more things as well. And one thing that I think is one thing that we've definitely realized is that we need to build up an infrastructure which handles a more general set of loops than what Poly will currently give you.
I was wondering if you have seen any positive effects of sharing your proxy apps in the test suite rather than keeping them to yourselves in your lab. Like, it's probably a bit of work to do that.
Yeah.
Did you see any positive effects for you for doing that work so far?
Oh yeah, thank you. So yes, I mean, we've definitely seen increased visibility. It's nice that we can now track these upstream. I should say that we've also had a lot of internal benefits from doing this, because it turns out that what we had before was we had a whole bunch of these proxy apps, on different websites. And if you wanted to use one, you had to go and download the thing, figure out how to build it, read the README to figure out how to run it. And then you could perhaps do some experiments. So we have a bunch of software technology projects across the DOE. And now, if they want to run these proxy apps, all they have to do is download the test suite and run. And so we've actually had a large benefit from that also, even internally.
Okay, I think...
Yeah,
Yeah,
Are you talking about decoupling the transformations from the analysis?
Yes.
Good.
okay, so...
Just make one comment.
Oh.
On the pragma side, I agree that we should actually try OpenMP, more OpenMP stuff, because all of those pragmas we created to run tests, not to people to use. So I don't want people to use Clang-specific pragmas or GCC-specific or ICC. I think it's a good idea to try to common them up, but if OpenMP is standardizing them, we should use OpenMP stuff, replacements, because a lot of the SIMD stuff that we did is in OpenMP already. It wasn't back then, but it is now. So I think maybe we should just move into whatever is standardized already rather than trying to standardize more things.
Yeah. I mean, as a practical matter, one of the projects that's funding this work is actually an OpenMP improvement project. So we definitely intend to experiment, see what works, and then based on that we will almost definitely propose a subset of it for standardization in OpenMP. So.
Okay, thanks. Let's thank the speaker again.